organizers, especially to Joel and Avishai for putting this wonderful workshop together over the years. And of course to Colin also for producing the program every year over the decade. And also want to congratulate Sandy and Joel for this great achievement, over 40 years of BFPR 84 papers. And I'm really grateful to witness your achievement on Monday evening, and just a little bit of glimpse to your luminous career. So I'm very happy to be here, and thanks for this opportunity, and thanks for your service to the community and your dedication to education and science overall. And also grateful to Rachel, who put together the Monday event. You did a wonderful job, and I'm happy to be here. Okay, so I'm going to tell you a little bit about the Agora efforts that we have been doing over the years, and as Ji-Hoon summarized very nicely, from the inception of Agora in 2012, I participated in this effort since 2013, and I've been here 8 times, so this is my 8th visit to Santa Cruz. Yeah, and so Agora gave us a framework to work on this project, and I think it's also true for many other smaller groups around the world who participate in this project. And for myself, I participated in this project using Gadget 3 code, Gadget 4 code over the years. So if you see here, when we started to participate this with my students in Nevada back then. And then, as Ji-Hoon said, there has been papers of Agora 2, Agora 3, Agora 4, 5. All these papers, and along the way, we also worked together in sync with the progress of the project. So when we were transitioning from isolated galaxy project to cosmological project, we started to develop this Osaka feedback model with Iko Shimizu, and then also made a transition to feedback model 2 and 3 with Yuri Oku in his PhD thesis. And now we're performing this crocodile suite of simulations with Galaxy 4 Osaka, which has also been implemented to the Gamer 2 code with his effort. And as Ji-Hoon said, we were happy to welcome everybody to Osaka last May, and 120 people gathered, and we had a very lively discussion, and also further to make the progress on the Agora project. So we hope to do this every few years in different places, so please join us in Osaka in the next 2 years or so again. All right, so here's just one quick demonstration of the crocodile simulation, which was Yuri's PhD thesis project. We performed a series of cosmological runs, just like the other groups, and then from different box sizes of 25 to 500 megapascal boxes with different physics. And in particular, in our simulations, we had options of choosing the top heavy IMF at low metallicities, which allowed us to say more about the recent implications from the JLFST observations. For example, anomalous abundance ratios, suggested for the high Z star clusters, etc. We're trying to address it with these models. So 13 species of chemistry using this CELIB chemical evolution model to couple to the Grackle. Variety of feedback model combinations in these different box sizes, which allows us to address which of the feedback is important for certain aspects of the observational probes that you're interested in. And we also have dust formation destruction with grain size evolution, which we have not yet to explore so much yet. So these are all useful for galaxy evolution studies. Like any other codes, we have these 2 modes of feedback with supernova feedback, kinetic and thermal. Kinetic feedback injects the momentum to interstellar medium, which is driving the turbulence. And the thermal feedback shock heats the gas around it by a supernova ejector interacting with the ambient medium, which produces the hot outflow and transport metals out of the galaxy. So because these cosmological simulations cannot resolve this adiabatic set of Taylor phase, we actually need to implement these explicit models of galactic wind models to produce hot wind. Okay? So we actually started with these very small scale Athena ++ mesh simulations of super bubbles, trying to look at how these bubbles actually expand into ISM, trying to learn more from this small-scale physics, and we actually came up with this unified time evolution model of the supernova bubble final terminal momentum, and managed to expand this into a low metallicity regime on top of the prior work that was done by Kim and Ostreicher 18 or so. So with this new prescription and feeding models of the terminal momentum, we found that there's actually a factor 3 enhancement in the momentum yield in the zero metallicity case compared to the solar metallicity. So it has a fair impact. Okay, and then okay. So with these models, we actually take this top-heavy IMF, not in the Agora collaboration where the IMF is actually standardized. In those cases, we use a Chabris IMF, but in our own trials of these simulations, we actually adopt sometimes this top-heavy IMF, which is actually coming from the first star simulations. They actually produce, based on the radiation hydro simulations, ab initio simulations of the molecular cloud collapse simulations. They predict the IMF. So taking that evolution and then coupled with this specific energy input boosted as you go to low metallicity and high redshift, we came up with this new models of the top-heavy IMF. If you implement this into cosmological model and then look at the galaxy stellar mass function, for example, as z equals 6, you actually suppress the star formation too much. Therefore, you actually underpredict compared to observed stellar mass function, which is actually in line with these recent feedback-free starburst models. If you don't have any feedback, you actually agree with this observational data at redshift 6. At low redshift, we actually do fairly well with compared to other cosmological simulations, like a low mass range and high mass range. Slight overprediction at the high mass range, but overall, we produce good results at low and high Z. Okay. So we have managed to put these together, these data sets from 25 megaparsec to 200 megaparsec boxes. These are all available on the web. And if you're interested, go to this website and check out. And we're happy to provide the post-processed data as well if you request. Okay, so using this simulation data set, we can look at, for example, the thermal evolution of the intergalactic medium, CGM. Like my student yesterday, Jan, examined the overall cosmological evolution of the baryon distribution as a function of redshift. We can now do this with FRB. And in a very few years, we're going to have thousands of localized FRBs, which actually directly shoot sight lines through these different thermodynamic gas, cosmological gas, and we can actually get a direct probes of these different thermodynamical distribution of the baryons across a fairly long range of redshift. Okay, so that is becoming a more direct study of the IGM, and which is exciting. Now let me turn to a few examples of the Agora efforts. So this Pablo Granizo is a visiting student in Osaka. Over the past 6 months or so, he made a very good progress testing the Gadget 4 code. So he's now doing all these ongoing calibration 4 steps for the simulation, including the isolated galaxy. But let me just show his recent results on the cosmological calibration step 4. And he's done very good work in following the Gadget 3 efforts. And in our simulation, we now can actually produce very consistent results to Gadget 3. Let me just fast forward this movie. It's a little bit slow. But depending on the input supernova energy models and the very slight differences in some of these parameters of the number of events of the supernova injection or the boost factor on the supernova energy yield, there's a slight timing difference that brings out these stellar mass differences at high redshift, but eventually it'll converge to the Gadget 3 result after z equals 4. So everything looks fine over here. There's a slight variations here, like we need to be a little bit careful about which one to use and how to compare. Okay. But these are all done. So we actually, in our group, we're going to make a shift from the Gadget 3 results to Gadget 4. And for the next set of papers, we're going to proceed further with the Gadget 4 code. Here's another examples of work led by another student, Kazuki Tomoru is another PhD student. He's now looking at the dwarf galaxies. And as Ji-Hoon said, I think the next project that Agora is going to pursue, it will be this high-resolution dwarf galaxy simulations. So this, for example, is already included in the Agora suite of dwarf galaxy. This is called M10Q, Quiet, and the Violent. And also there's another one we're trying to do. This is which may seem to suggest a little bit of a disky evolution on top of the left too. Okay, so these are in the pipeline. And for example, here's the initial result of the stellar to metallicity relationship compared to other efforts as well. We also reproduce those mass metallicity relationship. Also here is the stellar mass to halo mass relationship. All the other efforts also have a lot of data points, but we see that these dwarf galaxies are very sensitive to supernova feedback models because it's very susceptible to the explosions happening in the shallow potential well. So these are very difficult to produce, but we're getting there and building up the sample. Okay, and then the final few minutes, I'm just going to show you the AGN jet effort. So this has been going on for a little bit while, trying to compare this ENSO and Gadget 3 comparison with BKO and Abate with Yaldi. And we actually settled down on these 6 simulations with different treatments of the accretion, no accretion, bond accretion, or fixed accretion rate, whether we follow the mass removal from the black hole mass or black hole growth, etc. And for example, we're producing these plots, this ENSO density, Gadget density, and the temperature plots over here. So ENSO being a mesh code, it can actually look at the sharp edges of the expanding bubbles, whereas Gadget, you're actually shooting this Asian jet particles, therefore you kind of see a little bit blurry hot outflow coming out from the disk and differences in the phase diagram, etc. Okay. But you see this SPH code has a little bit of problem in these problems because it cannot really look at these shock fronts. So we're actually doing also a more detailed Asian jet simulation separately in addition to those large-scale galactic simulations, and we are examining very detailed structures of the cocoons and the jet lobes inside these expanding relativistic jets, and therefore we can look at this structural decomposition very, very carefully and then compare with the larger-scale galactic simulations to get more insight. Okay? So these simulations allow us to look at the very detailed evolution on the phase diagram, see how those ejected jet particles interact with the ambient medium, and see how they make these different components, subsonic, supersonic gas evolves on this phase diagram as it evolves on the scales of 100 mega years. And by having these information on small scales, we can learn what is missing in the larger scale simulations. Okay, so those are the efforts, and I think Mignon's going to present further his results. But I think one of the highlights that came out from these Agora collaboration past 10 years is his recent satellite problem, where he may have put in the final nails in the coffin of the missing satellite problem. So we're going to have a discussion later whether you all agree that the no more missing satellites problem or not in our community. Okay, so here's a summary, and thanks to Joel and other people who actually supported the Agora collaboration over 10 years. And I'll stop here and I look forward to future more discussion tomorrow. Thank you.
Thanks, Ken. Questions?
Thanks, Ken. This is really impressive work. So on the high redshift point that you made, most of the other simulations do reproduce the observations at redshift 6 and even up to redshift 10.
With the regular supernova feedback.
With the regular feedback. So do you understand why your results are so different in that regard?
So the suppression that we have is due to this very high injection rate per of the specific supernova energy. Okay? And if we turn off the supernova feedback, we actually go a little bit on the higher edge of the observed data. So other simulations are probably somewhere sitting in between of those no feedback edge and then the very strong feedback edge. So
yeah, I think if you turned off feedback in the other codes, you would get even higher.
Even higher?
I think so.
So
maybe there's something different with the cooling. That's the only thing I can think of.
Right. But we didn't do anything so much different with the cooling. So yeah, we need to check that a little bit more, I think.
Look into, yeah. Thank you.
Yeah. Other questions while the next speaker sets up? Okay, if there are no further questions, let's thank the speaker once again.